Hi, my name is Connor, and this presentation will discuss my thesis, which is based on the application of ground-penetrating radar and its potential for use in the railway for monitoring ballast fouling. The objective of this thesis is to determine whether ground-penetrating radar, or GPR, is a beneficial tool for monitoring the fouling of railway ballast. A long-term goal for this would be hopefully moving maintenance practices from reactive to preventative. Railway is a vital part of transportation systems across the globe. Millions of commuters catch trains on a daily basis, so it's obvious that the tracks need to remain in a safe and working order. Railway lines are also one of the main methods of transporting coal and freight, with Australia's heaviest rail network being around 33,300 route kilometres. Maintaining railway infrastructure requires significant financial investment, which is why railways are continuously searching for better ways to plan and carry out this maintenance. The scope includes completing a literature review into the fundamental theories behind ballast fouling and its effect on the track structure. The ground-penetrating radar system is examined, and its potential for application to ballast monitoring is investigated through data collection and analysis. The fouling output from the GPR will be compared with the outputs from the track recording car for the corresponding time frame, and a rate of contamination will be assessed using GPR runs at a 4-year interval. The track structure can be broken down into the superstructure and the substructure. The superstructure consists of the sleepers, rail, and fastening system, and the substructure consists of the subgrade, capping layer, and ballast. The main purpose of the track structure is to transfer the loads from the rail traffic to the formation as uniformly as possible. The loads are imposed onto the track at the wheel-rail contact point and travel down into the sleepers, which transfer the load to the ballast. The ballast then distributes this load onto the subgrade at a much larger surface area, with the capping layer acting as a separation layer between the ballast and the subgrade. All track elements are working together to facilitate this load transfer. The capacity of the track depends on how they interact. The geometry of a track signifies how tough a track is. It is usually monitored using a track recording car, which measures various aspects of the track's geometry and compares them without bias to produce condition indexes. The typical characteristics that it measures are the top or vertical alignment of the rails, the twist over 3 meters and the twist over 10 meters, the gauge, the horizontal alignment, and the super elevation. It also develops an overall track condition index. For the purpose of this investigation, the top and twist over 3 meters were focused on, as they are the most commonly affected by the ballast condition. Ballast serves many important functions, examples of which are listed here. This figure is a visual representation of the load transfer in the track structure and indicates how ballast spreads the loads onto the formation, or subgrade. Ballast also provides an easy method of track maintenance in order to correct track geometry in the form of tamping by rearranging the ballast particles and packing them under the sleepers. Ideal ballast should have a density equal to or above 2,500 kg per meter cubed and should be free of contaminants. It should be comprised of angular particles having no rounded surfaces to ensure that the particles lock together, at the same time leaving voids for drainage. In order for the ballast to perform properly, it needs to have a high shear strength and be resistant to weathering. The Australian Rail Track Corporation sets out a standard of grading in Australia, which dictates that the nominal size for ballast should be 60 mm and no more than 5% should pass through a 19 mm sieve, or it is considered fouled. While ballast facilitates easy, low-cost maintenance practice, it does have the tendency to deteriorate and become fouled, which causes further maintenance problems. Ballast fouling is when the voids which were initially used for drainage become filled with fines. There are various reasons why ballast may become fouled, including ballast breakdown, infiltration from the surface or subgrade, attrition, or insufficient drainage. Ballast breakdown is caused from a number of contributing factors. Ballast tamping and resurfacing is one of the main sources, as well as repeated cyclic loading from the trains. Infiltration from the underlying materials or subgrade generally occurs where there isn't sufficient separation between the ballast and formation, or the subgrade isn't adequate. This can lead to track pumping. This image shows an example of the track pumping. Once ballast has become fouled, the track structure as a whole begins to suffer and lose its desired geometry. This is because the ballast, which is supposed to deform elastically, enters the plastic deformation stage and no longer acts as it was designed to. As the voids fill with the fines from various sources, the drainage begins to become impaired. Once water is added to the mix, hydraulic erosion begins, which leads to a much more rapid fouling rate, facilitates attrition, and lubricates the particles, resulting in loss of track stability. Also, once the degree of fouling is high enough, the fines will dictate the behaviour of the ballast bed. Percentage voids contaminated, or PVC for short, is used to quantitatively evaluate how foul the ballast is using volume measurements and knowing the typical percentage of air voids in clean ballast. It has many advantages, including the fact that it doesn't rely on the masses of materials to calculate the extent of fouling. It also has the potential to predict the ballast life if all other maintenance data and property information are available. Ground penetrating radar, or GPR, is a widely accepted method of mapping surface conditions, including structures, erosion, and moisture content. It has been used in fields such as pavement design and bridge inspection, as it provides a non-destructive means of seeing what lies beneath. GPR uses various frequencies depending on the desired application, though for ballast monitoring, generally 2 GHz and 400 MHz frequencies are used. It produces a radargram similar to this one here, which can then be analysed and further processed if needed. The bright reflections you can see here indicate the surface of the ground, and then further down there's another reflection, not as bright, which signifies a change of material, such as the bottom of a ballast layer. GPR can be used for calculating PVC. This is done using a 2 GHz signal which enters the ballast voids and reflects off the particles, resulting in electromagnetic scattering. A relationship has been derived between this scattering and ballast fouling. As ballast becomes fouled, less scattering is evident, as can be seen here, compared to the clean ballast here, where there is more scattering, signifying the presence of air voids. The method of approach chosen in order to complete the data analysis was to first gather all necessary data. This included the GPR and track recording car data from 2011 and 2015, as well as any maintenance history leading up to and within the 4-year period. Step 2 was to compare the PVC outputs from the two sets of GPR data in an attempt to calculate the rate of contamination of the ballast. Following that, a comparison of the track recording car and PVC outputs was compared to give insight into whether the ballast fouling and track geometry had any correlation according to the two means of track monitoring. It could also suggest whether the track recording car could be used on its own, or whether the GPR was necessary to come to a conclusion on the track condition. To select appropriate data, some limitations needed to be set. Any section of track which had recently been undercut or resurfaced was ignored, as it would give false results in terms of foulness levels and track roughness. Also, data from different line types was collected, i.e. passenger only versus freight and passenger versus freight, coal and passenger lines. As external factors such as bridges, subsurface drainage, turnouts, diamonds and tunnels would affect track roughness as well as ballast condition, the locations were chosen where these were not present. So this is what the processed GPR data looks like in PDF format. The top two metrics give the various layer depths. If you look over here in the trackbed layer interpretation box, it gives you what each colour means. So the dark green corresponds to the base of the dominant trackbed layer for the centre, and then this one's for the shoulders. The next metric we have is the contoured depth to the base of dominant trackbed layer, and then there's the contoured ground surface. This gives an idea of what's happening either side of the track. So the track centre appears along the middle here, and then up here is the legend which tells you what the different colours mean. For example, this appears to be a platform, as it turns white, which means it immediately becomes higher than the centre of the track, and blue means that it's lower than the centre of the track. Next is the ballast thickness index. So this gives indication into where ballast pockets could be, with blue meaning that it's deeper than 600 ml, the ballast layer. So this makes it easy to go through and identify potential ballast pockets, and then you can check back up here for how deep it actually seems to be. So if you can see that, it appears to be talking about that little dip there. Next one is the layer roughness index, followed by the moisture likelihood index, and the last one is the PVC. This legend here gives an indication into what the colours mean in this bar, with purple being the most fouled and green being clean. The whole thing is a kilometre worth of track, and I've just put example change down the bottom here in metres. From site investigations, it seems as though the centre of the track gives the best indication into the actual fouling level, so that was used for the whole analysis. And this data also came in Excel format. So this is an excerpt of that here, and that gives the PVC values, the exact PVC values calculated in 5 meter increments, which is what each line is. Then it categorizes it into the corresponding PVC category, with again 1 or purple being the most fouled, over 60% fouled actually. This is an example of the outputs from the track recording car. The first 3 lines of data are going to be focused on for the analysis. These are outlined in red. Then the track condition indexes that I talked about earlier are circled in blue. SCI stands for top condition index, and there are 2 lines of this, one for each rail. The third is the twist, measured over 3 meters, and the twist condition index is abbreviated to WCI. The twist is essentially the changing cant of the rails. The overall track condition index, or TCI, is on the far right and gives an overall indication of the condition of the track. In order to analyse the data, it needed to be filtered and refined. This included filtering out any obscure values, such as percentages of voids contaminated, which were less than 0% or more than 100%. Also, any 100 metre length of track with less than 50 metres of usable data was disregarded. The GPR data was then sorted into 100 metre lengths, and the average change in PVC was calculated from 2011 to 2015. The average rate of contamination per 1,000 megagross tonnes was consequently found for each location using either the mean or median, depending on the normality of the data. This was completed using Minitab. This is an example of a Minitab output. The p-value gives an indication into whether the data follows a normal distribution. If the p-value is greater than 0.5, then it can be considered normal, and the mean can be used as an average. If not, then the median should be used. Locations A and B are sections of track which carry freight, coal, and passenger trains over the lines. They both follow a normal distribution, and so the mean can be used to find the average rate of contamination. Locations C and D were passenger-only lines. Location C had less skewed data, so the median was used to find the average, whereas location D was normal distributed data, so the mean found the rate of contamination. A summary of the rates can be found here. The track recording car versus GPR percentage voids contamination data needed to be filtered. This ensured no external influencing factors such as subsurface structures were included, as this could skew the track geometry data to say that it appeared more or less rough than it actually was, caused by the ballast. The track condition indices for sections with the same axle loads and tonnages were plotted against corresponding PVC values using Minitab. A regression line was then created in an attempt to determine whether there is a correlation between the track geometry and ballast fouling. This is an example of the percentage voids contaminated plotted against the track recording car data. The purple is indicating the fouled ballast, and as you can see where the fouled ballast starts, the track appears to become more rough. This is an example of the Minitab output for the track recording car data plotted against the PVC for each set of data. The p-value here, if less than 0.05, suggests that the independent variable, which is the PVC, is likely to be meaningful to the changes in the dependent variable, or the track recording car data. The PVC was plotted against the top condition index and the twist condition index, as well as the overall track condition index and the top condition index plus the twist condition index. This was to see which condition index had the highest correlation with the PVC. These are the results from the 2 datasets analysed to find if the track geometry is influenced by the ballast fouling. Dataset 1 indicates a correlation for most condition indices except the twist condition index, with the strongest correlation being the overall track condition. This suggests that the track condition is influenced by the ballast condition. Dataset 2, however, shows no correlation at all. Therefore, no conclusion can really be drawn about the track geometry when considering the PVC from the GPR data. However, this may indicate that the track recording car alone does not give insight into the condition of the entire track structure, but should be used in conjunction with the GPR for a full picture. In conclusion, the ground-penetrating radar may be able to give insight into the rate of contamination of the ballast, and therefore be a useful tool in planning maintenance and predicting the life expectancy of the ballast bed. However, further investigation should be carried out in this area. The track geometry car data versus the PVC was inconclusive as to whether the ballast fouling was having an effect on the track geometry. This said, the track recording car alone cannot give the complete picture, as it may indicate that the track is in good condition where the ballast may be severely foul. For this reason, GPR would be a beneficial tool in the railway. To further gain understanding into the applicability of GPR in railway ballast monitoring, future research suggestions are included here. Sections of ballast should be pre-selected and closely monitored over the length of time which the data is collected, ensuring that all maintenance works are accurately recorded. Detailed subgrade investigations should be carried out. Ballast samples should also be collected from various tracks with differing traffic types. The contamination level of these samples should be tested and compared with the PVC values that the ground penetrating radar produces to verify the accuracy of the outputs. Also, further data should be collected for determining the rate of contamination. This requires multiple GPR runs to give a more accurate result. Thank you for listening, and I hope this presentation was informative.